Okay, so we are going to work through, oops, sorry. I think it's 4 problems here. The first one is practicing with weak acid equilibrium. So we'll kind of review what you've been doing, but the catch here is going to be the assumption doesn't work. So like we did in the last chapter when we started with equilibriums where they were fit the 5% assumption rule, and so we could simplify our math and calculate from there. This first one we're going to work out, it doesn't quite fit that assumption, and so again you'll have to do the more complex math, but you all can handle it just fine. So we're going to start with this one. The value of Ka for citric acid is given there. To simplify our work here, we're going to call citric acid HCA. So we're going to calculate the pH of 0.200 molar HCA solution. So the first thing we want to do always is to write out our little equation, the reactions of interest. Let me get my pen here. Okay, there we go. So we have HCA, which is representing, sorry, did someone say something? Okay, so HCA, citric acid, and it's going to break up into the citric acid ion plus the hydrogen ion. So that's the way the dissociation equation looks for this particular reaction. We also know that we have water, which remember is amphoteric.
Headphones to work.
And so it is going to break into hydrogen and hydroxide. So it also could act like an acid or a base. But remember, the Ka value, or we call it the Kw, is 1 × 10⁻14. So it's much less than the Ka value for citric acid. So just like you have been working, the citric acid here is going to be the major contributor in the equilibrium to the pH. So we're going to just use this equation. We're going to ignore the water part. So the Ka is going to be products over reactants. This is the equilibrium expression like we have done before. And then we can, for purposes of work, I'm going to rewrite this equation below. And then we'll do an ice chart. So initially, we have a 0.2 molar solution. We know that initially there's no Ca or H. It's a 1-to-1 relationship, so it's going to be negative X change plus X plus X. And then the final at equilibrium, adding up our columns here. There we go. So now we can use the Ka value up here to solve for X using products, which would be X squared over reactants, 0.200 minus X. When we solve for X here, I'm just gonna, with the assumption. So with the assumption, if we ignore the X on the bottom here and just do X squared over 0.2, we end up with the hydrogen and the citric acid being 1.22 times 10 to the negative second. If we do our little calculation to see what the percentage is, so I'm just setting up a percentage, this value over the original value, how much of it is it by percent? You get 6.1%. So the assumption here doesn't work because it's over 5%. So basically we have to scratch that and start over. So I can do that easily by erasing. I can pause if you guys are taking notes. Do you need me to pause? Okay, I'm just gonna erase it. Sure. If you're just watching, that's fine. So back to the drawing board, we have to then use all of the math. So the algebra. Sorry, I keep trying to erase. 7.45 times 10 to the negative fourth, and bringing the denominator up by cross multiplying. And then we're going to get, and I'm just going to do the math here for you, x squared plus 7.45 times 10 to the negative fourth, x minus 1.49 times 10 to the negative fourth equals 0. So there's the quadratic form, and then you can solve it using the quadratic formula. When you do that, you get x equals 1.18 times 10 to the negative second. This is going to be equal to the hydrogen ion concentration. And remember, calculating pH is equal to the negative log of the hydrogen ion concentration. So when you take the negative log of 1.18 times 10 to the negative second, you get a pH of 1.93. So there you have it. The calculation to pH. Of course, you can check your results by plugging the hydrogen ion concentration back in to the Ka value to see if it fits to calculate out that Ka value. So you would just basically plug the right side of this equation back in and see if you get the given Ka value, which in this case you do. And so this number that we calculated is good for this particular equation. So there's nothing different here than what we did in chapter 13, except for the fact that you're dealing with acids. So the process is very similar. So we're going to check our assumptions always and make sure that they work under the 5% rule. And then if they don't, we have to go through and do the quadratic equation to solve for it, or whatever is necessary. Any questions on that? All right, let's look at the next one, which is the pH of a mixture. So if we have a mixture of weak acids, how do we deal with that? So remember in the beginning, the very first thing that you do is determine what substance in the solution is causing the greatest effect on the pH. If you can kind of narrow it down to one species, then our process is really easy. We just fall back on what we've been doing. Like when we sort of ignored the water in our previous examples here, if one of the acids isn't really contributing to the pH, then we're going to just ignore them. So let me work this one through, and we'll see where it goes. Calculate the pH of a mixture of 2 molar formic acid. So let's start there, and we'll just write out the dissociation equation. Oops, not a plus sign. It should be a, there we go. And we have the hydrogen ion, and then the COOH, which is the carboxylic acid ion here. And it gives you the Ka value. It's 1.77 times 10 to the negative fourth. You also have 1.5 molar hypobromous acid. So that would be HOBr. And we have hydrogen plus the bromite ion. Or it's actually the hypobromite ion, sorry. 2.06 is times 10 to the negative 9th is the Ka value that's given up here in the equation. And then of course we have water, H2O, because it's aqueous, plus OH here. And we know the Kw, this one you should have memorized, is 1 times 10 to the negative 14th. So here we see that the dissociation of formic acid is by far the most important supplier of the hydrogen ions based on the Ka value. Notice these other two are much smaller. And this goes back to Le Chatelier's principle that will dictate that the dissociation of the hypobromous acid, the second equation here, and the water, the autoionization of water will be suppressed. And so we've reduced our problem to one acid. We've chosen the formic acid as the major contributor here. So we'll go forward using that. And initially we have 2 molar formic acid. We have none of these. It's going to be minus X plus X plus X. It's going to be 2 minus X, X and X. And then we plug that into our equation. The Ka value given for this is 1.77 times 10 to the negative fourth. That's equal to X squared over 2.0 minus X. And we can solve for X using the assumption. So assuming that it's a small change, we can ignore the minus X here and solve for just X. And when we do, we get 1.8 times 10 to the negative second. And checking that So I'm just going to plug this in over 2 times 100. And that gives me a 0.94%. So our assumption works. And now we can calculate the pH. So yeah. The pH is equal to the negative log of 1.88 times 10 to the negative second. And that gives us 1.73. So that is for the hydrogen ions, of course, of, no, I'm sorry. This is for the formic acid. It asks us to calculate, if we go back up here, both the hypobromite ion and the hydroxide ion at equilibrium. So we are not finished here. We have the pH, but we haven't really calculated what we were asked for. So we need to go back to these two equations that we ignored. And I'm going to do it over to the side in red. So the K value for the hypobromite would be represented by this equation. So we plug in what we know. 2.06 times 10 to the negative 9th is the K value. We know the hydrogen ion concentration is 0.0188. And originally, the concentration of the hypobromous acid was 1.50. It's going to be 1.50 minus X, such as this, but we're going to ignore the X because our assumption worked. So we're going to assume it works here too. And we're going to have X equals then 1.6 times 10 to the negative 7th. And since X is going to be the OBR minus, we have calculated that molarity then, or that concentration. Now, we're not done. We still have to calculate the hydroxide ion concentration. So we're going to this equation here. But we have a little bit easier calculation here. Remember, pH plus POH equals 14. So we can plug in our pH, which is, oops, sorry. Our pH, which is 1.73 plus POH equals 14. So doing a little algebra, we can calculate the POH, which is 12.27. And then remember, POH equals the negative log of the OH concentration. So to calculate the hydroxide concentration from the POH, you're going to take 10 to the negative 12.27. And that will give you the OH concentration. And I've got to make some more room here. So I'm going to erase that. And when you do that, you should get 5.4 times 10 to the negative 13th. All right, any questions here? All right, let's look at the next one. This one's simple, so we won't burn your brain out too much. So it says determine the formic acid percent dissociation of formic acid given in the previous problem. So when we're talking about percent dissociated or percent dissociation, we say it's equal to the amount dissociated in terms of molarity divided by the initial dissociation, again by molarity, and then times 100. So if you go back, we need the amount dissociated and the initials from previous. So the amount dissociated would be equal to this number here. And then the initial would be this 2 that we had of the formic acid. So that's where we get those numbers. So percent dissociation equals then 188 over 2 times 100. And you'll notice this looks a lot like the assumption equation that we just used to prove our assumption was correct. So that's 0.94%. And that's it. So when you're proving your assumptions, you're actually calculating percent dissociation. How much was dissociated in the equation? So that's a pretty simple problem there. Let's look at then taking percent dissociation and calculating a Ka from that. Whoops. Okay, so here we have a problem in a 0.5 molar solution uric acid. The percent dissociated was 1.6. We're going to calculate the value for Ka for the uric acid. So it says that 1.6% was dissociated. Remember that is equal to the percent of the ion concentration. In this case, if we look at the dissociation equation, it would be H plus this ion here. So how much of these were dissociated? Initially, it's 0.5 and then times 100. So this is a percent. Now in this case, you could pick either H or the uric acid ion here because they're going to be equal. They're both going to be X. So when you do this, you get 8 times 10 to the negative third molarity. And now you can, so you're kind of going backwards. You're going to calculate Ka, which the expression is hydrogen ions plus C5H3N4O4 over this uric acid. So then you just plug in what you know. Ka is equal to, both of these we calculated from the percent dissociation equation. So this is actually going to be these, or you could just say this number squared. And then on the bottom, might be useful to you to do an ice chart so you can see. So initially we have 0.5 molar and 0, 0, right? And then the change is going to be minus x plus x plus x. We've calculated the x. It's that. The 0.5 minus x. So here, when we do this at the bottom, we're going to have to take into account that this changed at equilibrium by this amount here. So calculating Ka then from that, we get 1.3 times 10 to the negative fourth. So kind of doing things a little bit out of order. When you have dissociation, you're finding the change really, and then you have to apply it in the calculation of the equilibrium expression or equilibrium constant.